So one important announcement. I had written earlier in Teams that next week is the test window as specified by the institute. So your first theory test would be then, and we are planning for Wednesday. So next Wednesday, same time, 12. Okay, that will be your class test. I will send out a formal set of instructions, etc. later, but let me just tell you a few things. So we plan that it will be a proctored exam. That means during the time of the test, you will have to keep your video cameras on and sit in front of your video cameras and then write the answers on a pen and paper using pen and paper. And then you will scan and upload your answer script to Moodle. Okay. So it will be a proctored exam as in, so there are 10 or 11 TAs. Each one of them will be present, say in a Google Meet link or something like that. And you will be given these online exam halls. Each of you will have to join one exam hall, which you will be told. And in that hall, you will have to keep your video cameras on throughout the duration of the test. And and you write your answers using pen and paper. And then you scan and upload the answer script to Moodle. Okay. So this is how we had taken tests last year also. And it more or less turned out well. So detailed instructions will be given to you, like which links to join, etc. But yeah, this is the basic setup, a proctored exam. And syllabus also will be told to you. So, syllabus will be told to you very soon. Any questions about the test? So the test will be on Wednesday, next Wednesday, this time, like 12 noon. And it will be around 1 hour duration. So usually what we do is we give 1 hour writing time and maybe 10 minutes additional time to upload your scripts. That we will discuss, but yes, it will be around that time. So 1 hour to 1.5, 1 hour 15 minutes total. Any questions about the test? Okay, Nisarg is asking, can the test be kept not on Wednesday? Why, Nisarg? Unmute yourself and say.
So like there are two subjects which don't have any other slot in the whole week. So it's very much necessary that their test will probably take place on Wednesday only. And other than that, like so the whole of Wednesday will be
Which
very like
subjects?
packed. So it's the uh, uh, bioscience subjects like EVS and bioscience.
So bioscience subject, another test will be on Wednesday.
Like both subjects are on Wednesday only.
Both subjects? You mean you have taken 2 bioscience subjects?
No, like it's mandatory for us. One of them is bioscience and one of them is EVS.
Okay.
The whole batch has them. They are mandatory subjects.
Okay, and they're on Wednesday.
Yes, sir.
I'll have to talk with Professor Mondol and get back. Okay. So fine, we will see. So maybe Thursday or Friday, then we have to see. Okay, I'll talk with Professor Mondal and get back. But in general, whenever the test is one of these 3 days, it will be Rajat. So okay, good. Anything on Friday? I'm sure couple of tests. So see, yeah.
So, sir, for me, Friday will be free. I mean, for me, I don't have any tests on Friday.
I'm
So,
sure someone else has. So okay, see, it's basically a pigeonhole principle thing. So we'll have to take the test either on Wednesday or Thursday or Friday. Right. So I can understand that Wednesday at least what Nisarg said, it seems many people have those subjects. Like, again, if it is not so, I mean, we can take a poll if you want, like Wednesday or Thursday. Na? But yeah, I mean, I'm sure there are other, every day we'll have other tests because the institute has told all subjects to take class tests within those 5 days, right? So yeah, I mean, it has to be either, I mean, I really think we cannot get a day where there will be no other tests. So yeah, so so you know the schedules of the tests. So start preparing a bit early instead of waiting for the last day. So yeah, so yes. So okay, again, is there anyone who feels Wednesday is better? Okay, fine. I can, if it is the case that all of you have other, so the reason we were preferring Wednesday is that it's 12 to 1. So even if it can go up 15 minutes later, there will be no immediate class. That's why we were preferring Wednesdays. If then I'll talk to Professor Mondal and get back, but it has to be one of those days, right? So I mean either Thursday or Friday we have to. Let me ask this also. After, so let's say the Thursday class 11 to 12 or Friday class 9 to 10. Do any of you have classes immediately after that? Right after the OS class on Thursday or Friday? Does anyone have classes immediately after? Okay, so Friday it seems no class right from 10 a.m. Fine. Okay, then what I understand is Friday you don't have any class right after the OS class. So I'll talk to Professor Mondal and get back. Yes. Okay, let's start our discussion now. So I hope the slides are visible. Okay. Okay, so you're discussing process synchronization, and we have basically understood what the problem is. That basically, whenever two cooperating processes are updating some variables in shared memory, let's say, we, I mean, so we while writing in a high-level program, we just write one statement, say counter plus plus or counter minus minus. But actually, that can lower down. It can be translated into 3 machine instructions. And the problem is that we do not know when a process will be deallocated from the CPU. So it is possible that one process loads a variable in the memory. Sorry, one process loads a variable from the memory to the register, but and it changes that variable in the register. But before it can write back the register content to memory, it is deallocated from the CPU. And another process comes in. That process also does the same thing. So it loads a value from the memory to the register, changes the register content, but before writing back to the memory, it gets deallocated from the CPU. So these things happen, and I mean, these things can happen quite regularly. And therefore, we can get such conditions which are called race conditions. Essentially, the final, what is, I mean, so a bit more formally, what is a race condition? The outcome of execution depends on the exact order in which the instructions get executed. Okay. By the way, so does this remind you of something you have studied in some other course, maybe? Another place, another application where such race conditions can be a big problem. Pipelining, okay. Okay, so Ravi, can you unmute yourself? What about pipelining?
Hello.
Yeah.
So there also in the CPU pipelining, we will get the race conditions between operations.
Mm-hmm. Okay.
Say if one register is being used in one instruction and in the next instruction it is being updated, so there will be conflict. So if it is like accessing the register before one is updating it, then there will be race conditions.
I see. But the programs are written sequentially, so why should that be a problem? As in, like, of course, the instruction to load a register comes before maybe the one to update it. So why should there be a problem? Are you trying to say before a register is updated back, the next instruction tries to
Yes, sir.
access it, right? Okay.
Yes, sir.
Agreed. That is one case. Okay. Anything else like is done in pipelining which might lead to race conditions? Okay, fine. We'll come to it later. Fine. Okay, Deep is telling forwarding. Okay. So basically, I mean, forwarding is a way of mitigating this, right? Like the value is forwarded in advance to some other instruction, kind of, right? Okay, fine. So again, asynchronous digital circuits may also be fine. I mean, the thing that I was having in mind. Yeah, okay, Deep, fine. So forwarding is not actually a reason for maybe race conditions. It is a way to mitigate it. Fine. So the thing that I was having in mind have you done a database course? DBMS, database management? Okay, doing now. Fine. So I don't know if these things have been already discussed in DBMS, may come later, but you will see that this kind of race conditions can be a huge problem in databases because, so let's say the same thing happening as shown in this slide, say two transactions like in a bank, let's say you have put in 1,000 rupees in your bank account or okay, yeah, and okay, so maybe you have withdrawn 10,000 rupees from your bank account. Someone else has credited 5,000 rupees to your bank account. So these two transactions will ultimately access the same account. And if something goes wrong in between, say in one transaction, something goes wrong, then the other transaction might get affected, or maybe that won't get affected, but the final state of the account might get affected, right? Have these things been discussed in database course yet? Exactly. Preet Kumar, yes. So just maybe unmute yourself and say what has been discussed about this in database.
So just what you said, the example was also the same one discussed, that suppose in a banking application, if one or more updates take place at the same time or filed in very near to each other, then we can write atomic keywords to ensure that one operation is perfectly completed after the next one begins.
Yes, so basically, if this happens that two different operations are accessing the same data or account, then if it might happen that the outcome of execution depends on the exact order in which the instructions get executed. That might lead to race conditions, and therefore steps need to be taken to prevent that. So yes, what Preet Kumar said, it's actually correct. So atomic updates or operations is one key mechanism by which such race conditions can be avoided. Okay, so actually in this lecture also we will talk about such terms, and in the database course also possibly you will get to hear such concepts. Try to create a mapping between the concepts because essentially the problem is the same. Of course, OS is, or in the operating system course, we will be talking at a bit of a lower level, at the instruction level. In databases, you will be talking at a higher level because after all, database is an application. So there you will talk about transactions, etc. In operating systems, we are talking about instructions at the instruction level, a bit lower level. However, the problem remains the same. That is, maybe two different instructions or transactions trying to update the same shared variable or value or account. If it is the case that the final state of the account depends on the exact ordering of in which the instructions or transaction processed, then there is a problem, right? Let's say, as I was telling, like maybe you withdrew 10,000 rupees from your account, someone else credited 5,000 rupees. So after both these transactions are over, ultimately the final state should be your account has been debited by 5,000 rupees, right? Because you subtracted 10,000, someone else added 5,000. So I mean intuitively that should be the final outcome. But if the final outcome starts depending on the order in which the instructions get executed, then there is a problem. And that is what was demonstrated in this slide, this one, that because I mean, processes can, in our OS context, since processes can be deallocated from the CPU at any point of time, these things can happen. Okay, fine. So yeah, so this race condition can come in different contexts, like even at the application level or at OS level. And formally, this is called a critical section problem. Okay, and we discussed that the critical section is that part of a code where a program is updating some shared variables. So in order to what about the critical section problem? We have to ensure some conditions. Conditions like these, which we discussed, like mutual exclusion is the main thing that we are talking about. That if at least, at most one process should be executing in its critical section at any point of time. That means if one process has started executing its critical section, no other process should be allowed to enter its critical section, even if that process is currently not executing, right? So maybe process PI has indicated that I have entered my critical section. It is taking some time in critical section, therefore it may be swapped out of the CPU. It may be again resuming, some other processes may come in between. Whatever it is, even if process PI is not executing right now on the processor, no other process in this set who are all updating the same shared variable should be allowed to enter its critical section. Okay. Additionally, there are some other conditions also which need to be satisfied, like progress and bounded waiting. Essentially, one process should not be made to wait indefinitely before entering its critical section because other processes are going on entering their critical section. Okay, so these things we have discussed. Now let us actually discuss a solution to a critical section problem. There is no one solution, but the first solution we discuss, we will point out some flaws and then go for other solutions. So the first solution is called Peterson's solution. And this is a pure algorithmic or software based solution. Okay, note this point. This is a pure algorithmic or software based solution. I mean, no special support from the operating system or hardware is assumed. This is purely an algorithmic or software based solution. And this solution is restricted to two processes that alternate execution between their critical section and reminder section. Okay. So critical section is where the shared variables are being updated, and reminder section is the rest of the code. So we expect that, like, suppose there are two processes, a P0 and P1. Once P0 has to enter the critical section, again then P1 has to enter the critical section. Again P0 has to enter the critical section, P1 has to enter the critical section. Some application like this. There, Peterson's solutions is meant for that kind of a situation. Okay, and it assumes that the load and store machine language instructions are atomic. That is, cannot be interrupted. See again what Prith Kumar mentioned. You are also coming across this concept of atomicity in database course also. Here also we will talk more about atomicity going ahead. So essentially an operation or a instruction being atomic means either it will be completed basically it means if it is started it will be completed, and if it cannot be completed it won't be started at all, right? So that is atomic. So either, just like at one point of time in history, it used to be thought that an atom cannot be divided. So this term atomic came, that an instruction will either not be started, and if it is started, it will be completed. So that is an atomic operation. Okay, so what is the Peterson solution? Essentially, there are two variables. One is an integer turn, usually initialized to 0, and that there are two flags, okay, which are initialized to both false. The variable turn indicates whose turn it is to enter the critical section. As I said, there are two processes, P0 and P1. Whose turn is it to enter the critical section now, P0's or P1's? That is what turn will be used to indicate. And this flag that is used to indicate if a process is ready to enter the critical section. Right? So if flag I equal to true implies that process PI is ready to enter the critical section. That means the PI is saying that I now want to enter the critical section. Okay. Now let's see the pseudocode. So according to Peterson's solution, every process follows this kind of a flow. It first sets flag I equal to true. So remember, this is the code for process PI. Okay. It first sets flag I equal to true. Then it sets turn equal to J. And then it checks while flag J and turn equal to J do nothing. That means this is a waiting. Okay. And then there is a critical section. And finally the exit section where it has to indicate that I have now completed my pass over the critical section. There flag I equal to false. And then the remainder section. So intuitively what is happening? Process PI is indicating that I want to enter the critical section. So it is putting flag I equal to true. But it is not immediately entering the critical section. Rather, it is giving the other process the turn. Okay, so J is the other process. So PI and PJ. Okay, so PI is indicating that I want to enter the critical section, but it is not entering immediately. Rather, it is giving the other process the turn. Okay, and then it checks this condition. Okay, while flag J and turn equal to J. Yeah, so what is going on here? Okay, turn equal to J, I understand. What is flag J? Who set this? What is its value? Exactly what Ashutosh mentioned. Flag J will be set by the other process. not by PI, but by PJ. Okay, so don't get confused by like flag J isn't even initialized. What happens? I mean, okay, flag J is initialized at the beginning with false, but that's basically this process is not setting flag J. Flag J will be set by the other process. Okay, so this process is giving a turn to the other process to enter its critical section. And so what does this statement mean? What does this statement mean? So Ashutosh, can you explain? What does this statement mean?
I'm so sorry, if flag J is true, that means that most probably PJ will be in the critical section, and if turn equal, and I mean,
Okay,
yeah.
okay, wait. I want you to be a bit more technically correct. Flag J equal to true immediately means PJ is in the critical section. No, because see, here flag I was set to true, but that does not mean PI has entered the critical section. So be a bit more technically correct. What does this statement mean? So the answer is written in this slide. What does flag J equal to true indicate?
Yeah, I mean, it won't immediately enter, but like it is expressing its interest in being entered
Exactly.
in the critical section.
So PJ has also expressed interest to go into its critical section, and PI has given PJ the turn. Right? Yes, what Ravi also said. So this line means that PJ, the other process, has expressed interest to go into the critical section, and this process has given you the turn. Right? Like a pehle aap kind of scenario. So in that case, PI waits. Right? And when will it come out of this loop? When will it come out of this loop? Like, sure, I mean, from C syntax, we know that when one of these conditions are false, but I'm not talking about that. I'm asking like intuitively, when will it come out of the loop? Maybe Ravi, you can answer. Yes, after process J exits from its critical section. So after process J exits from its critical section, it will put this line, that means flag J equal to false. Okay, and then process PI will enter its critical section. Okay, so hope you can visualize it. If not, I have in the next slide, I have actually written down both these processes. So see, this is the two processes. Just take a minute to go through and understand what is happening. So each process first expresses interest to go into its critical section, but then gives the turn to the other process. And as long as the turn is given to that other process and that other process has also expressed interest, this process waits. So let's say P0, first it says that I want to enter my critical section. It gives the turn to P1. And as long as P1 has also expressed interest to enter the critical section and the turn has been given to P1, as long as both these are true, P0 waits, does not enter its critical section. Right? So when does it enter the critical section? Most probably when P1 has completed the critical section and has set flag 1 equal to false. The flag 1 equal to false means P1 has done this pass of the critical section. So it indicates that I'm right now I'm no longer interested in entering the critical section. So then P0 can enter, because then when this happens, flag 1 equal to false, then this while loop will become false, this condition in the while loop, and P0 can enter the critical section. Okay. And similarly, after P0 completes its critical section, it will indicate flag 0 equal to false, then P1 will be able to enter, and so on. Okay. Now, Peterson solution is theoretically a correct solution to the critical section problem. Because mutual exclusion is preserved, process requirement is satisfied, and bounded waiting requirement is met. and you can prove this. So I am leaving this as a task. Look up the book on the internet. You can actually prove that Peterson solution is, obeys all these conditions. So PI specifically enters the critical section only if either flag j equal to false or turn equal to I. So it can never happen theoretically that PI and PJ both have entered the critical section. Okay. Yeah. Okay. So any questions? Okay, if not, let me proceed. So Peterson's solution is theoretically a correct solution. However, in practice, there are problems. And the problem comes in because computer architectures are being made more complex. So just like you were mentioning things like pipeline stalls and forwarding and all, possibly in your computer organization architecture course, you have also come across out of order execution. Have you? Have you come across out of order execution? Specifically in pipelining and all that. Okay, in compilers. Okay, fine. Okay. In compilers. Okay. Yeah, maybe. Okay, sure. Okay, so the issue is that modern architectures allow out of order execution. Because if it sees that there is no dependency of one particular instruction, like it can be executed earlier than the other instruction, specifically to prevent pipeline stalls and all, then modern architectures will do that. Okay? So maybe one, so there are two instructions. I'm just making up an example. Suppose there are two instructions. Instruction one actually requires some value which has not been updated yet. So but instruction 2 is not dependent on any other value. So if instruction 1 is performed first, there might be a pipeline stall because that value is not updated yet, the value which is required by instruction 1. But instruction 2 does not require any such value which is being updated. So modern architectures do allow instruction 2 to be executed before instruction 1. Okay. In this kind of architectures, Peterson solutions can fail in practice. How? Let's see. The thing is, these two statements which are marked in red here, assume that they are executed out of order. That means first turn equal to 1 is executed and then flag 0 equal to true. Then what can happen? Let's see. So yeah, again, you have two processes, P0 and P1, and assume that the first two statements marked in red are executed out of order. So first P1 says turn equal to 0. Okay, P1 first says turn equal, this is executed first, turn equal to 0. And then there is a process switch. P0 starts executing and first the turn equal to 1 is executed. Then P0 goes on computing, it sets flag 0 equal to true. See, this is out of order execution, okay, which is possible in modern architectures. And then P0 enters the P0 starts the while loop. Okay. However, the problem is that it comes out of the while loop immediately because flag 1 is false. See, P1 has not been able to set flag 1 yet. Okay, understand? P1 started executing, but due to out of order execution, this statement turn equal to 0 got executed without executing flag 1 equal to true. And then the processor shifted to P0. So when P0 comes to the while loop, it will immediately come out of the while loop since flag 1 has not been set by P1. And therefore P0 enters the critical section. Okay. Now let's say again there is a context switch and P1 starts executing. So P1 has already executed turn equal to 0. So now it will execute flag 1 equal to true. And it will start checking whether it can enter the critical section. Now P1 also sees it need not wait because turn is 1. Okay, remember turn is 1. And therefore P1 also enters the critical section. Right. So in these situations, Peterson solutions may fail in practice. Though theoretically it's perfectly fine because you don't expect instructions to be executed out of order. But modern architectures allow that. And that is why Peterson solution is not enough. Okay. So in order to prove that a particular solution to the critical section problem is not correct, you just have to show one example situation where multiple processes can enter the critical section. If you can show that, that means this process is not guaranteed to be successful. Okay, so so I hope you understand the problem. If not, ask. But what do you think is the key cause, or what is a way of coming out of it? The answer we have discussed earlier in class today. I'm basically asking, I hope you understand the problem with Peterson solution. What do you think is the key cause for this? And the same question is that what extra is needed so that such situations don't happen? And we have discussed this earlier in the class today itself. Okay, Deep is telling signal hardware to not reorder. Okay, that's a good solution, good suggestion, but I'm not sure if it can be done. So that way, if that were possible, we could also have signaled the scheduler not to schedule some other process before this finishes. But unfortunately, these things cannot be done. Okay, what Ashutosh is saying, that is more towards correct. So Ashutosh, can you explain your answer?
So sir, basically this problem occurred because like in P1 turn was set to 0 and P0 set turn to 1, but in P1 flag 1 was not yet set to true, and that's why P0 entered its critical section, right? If we could have set flag 1 equal to true and turn equal to 0 together like atomically, then it would not have entered its critical section. P0.
Perfect. Good. So see, we have to accept that processes can be allocated the CPU at any point of time we cannot control. Similarly, we have to accept that modern architectures will allow out of order execution. We cannot control it. What we can control though is exactly what Ashutosh said. If we could have ensured that these two instructions happen together, then the problem would not have arisen. Okay. So essentially what we need is atomicity. We need some guarantees that maybe there is a particular instruction which either it will, if it starts, it will complete. If not, it won't. There will not be. So I mean, globally, you cannot tell a scheduler, oh, don't move. I mean, don't deallocate my process from the CPU. But in that time instant, like just for the duration of that instruction, there should not be any like other processes coming in, etc., etc. So it's an atomic operation. Either it does not start, or if it starts, it completes. Nothing happens in between. right? For this, we need hardware support. Okay, so essentially, we need specific atomic hardware instructions. So we will discuss several solutions going forward, and all of them are based on the idea of locking. That is protecting critical regions via locks. Okay, you might say, okay, another way could have been to disable interrupts, but again, that is not a very feasible solution. Rather, modern machines provide special atomic hardware instructions, which are not interruptible. So within that duration, within that small duration, when this instruction will be executed, there will be no interrupts. That means either this instruction will not even start to execute, or if it has started, it will complete. Nothing will happen in between. So essentially, remember again, Peterson's solution was a pure software solution, algorithmic solution. So again, theoretically it is correct, but because modern day architectures allow all these things like processor context switch at any point of time, that means preemption, then out of order execution. Because modern processors allow all these things, just an algorithmic solution would not be enough. You need this hardware support. You need atomic hardware instructions. So essentially, there are atomic hardware instructions which are either test memory word and set value or swap the contents of two memory words. Okay. So the general structure of the solution of a critical section problem is like this. Before entering a critical section, you acquire a lock. And after you complete your critical section, you release the lock. The thing is, this acquired lock, this should be atomic. So this is just a pseudocode. We will see some examples, but essentially that part is atomic, this acquire lock thing. Okay. Just one example. Just a minute. Okay. So yeah, a test and set kind of instruction. So let's say this is the instruction. So let's say test and set. And there is a Boolean pointer it takes as a pointer to a target variable called target. And so RV is a local variable which reads the value, the existing value of the target or the previous value of target. And then this function sets target equal to true and then returns RV. Right? Now this whole thing that you see, it seems like 3 instructions, but it is actually not. This whole thing is executed automatically. And importantly, it returns the original value of the passed parameter and sets the new value of passed parameter to true. Okay. So important to understand, we are writing this as a C pseudocode for better explanation. But actually this is a single low level instruction. Like say TAS R1 0000. So essentially this will set the value of R1, that register, to the 1000th location of the memory, and the 1000th location of the memory will be set to 1. Okay, so this is actually one instruction in MIPS architecture, which is a very well-known architecture. In MIPS architecture, we have a machine instruction like this. Just for the sake of explanation, we are writing it like a pseudocode showing this kind of 3 statements. But actually, it's a single instruction, which is atomic. That is the important part. So either these 2 things would be done together, or they won't be done. Neither of them would be done. Okay. Okay, so we will discuss such locks going forward. Okay, so this is not the only one. There will be multiple such locks. So how is it used? Let's say like this. So if you have such an instruction like test and set, then this is your entry section. That means this is your entry section. This is what you do before entering the critical section. You say test and set and then a variable lock. While this is true, you wait. Why? Because remember, going back, what is returned by this is the previous value of the target. Okay, what is returned is the previous value of the target. So if the return from this test and set is true, that means someone else was already locking. Okay, then you should wait. Okay, so when should you proceed? Coming back here, when should you proceed? So you have tried to set the lock. If it was already true, wait. However, if what was returned by this is false, that means no one else was locking and you have been able to set the lock. Therefore, you enter the critical section. Okay. So the key idea to understand here is this is an atomic operation. You set the lock and you get the previous value. If the previous value is also true, that means someone else was locking, so you wait. However, if the previous value is false, that means no one was locking, you have been able to lock. Therefore, you can enter the critical section. And finally, when you are done with the critical section, you say lock equal to false. Okay. So this is like if you have this kind of an instruction, which is atomic, then handling the critical section becomes simpler. Right. Okay, so I'll stop here today. Any questions, then ask. Okay, then we'll continue tomorrow. Discussion. Thanks, everyone.